Welcome to a video tutorial that reviews valence electrons and the periodic table, and then helps us connect this to the formation of ionic and covalent compounds. Let's get started. So it's important to remember that the chemical properties are determined by the number of valence electrons. But the great thing is that the elements are arranged in the periodic table so that they have the same number of valence electrons per column or group. So the number of valence electrons can be determined from the group number at the top of each column. We can show the valence electrons as dots around the central atom. So as we look here, we see that this is group 1. So all of these elements, and I'll use hydrogen as an example, they all have one valence electron. Right? So the main thing here is the group number equals the number of valence electrons. So then if we get to make the second row, or the second column, the second group, right? So then they have 2. So I'll use magnesium. There's 2 valence electrons. Now we're going to be focusing on the main group or the representative, so we'll skip the transition metals. When we get to boron, there are 3 valence electrons. Carbon will have 4, right? Because group 4, you can see the Roman numeral 4A or 14. So we just look in the ones place, right? So group 5 or group 15. So for nitrogen, I'll put it up a little above, 5 valence electrons. Oxygen, group 6 or 16, 6 valence electrons. Group 7, the halogens, will represent those as an uppercase X. That represents all the halogens, have the 7 valence electrons. And then, of course, when we get to the noble gases, they have the octet. So we don't have to worry about those because they're inert. So the main thing here is that finding the group number at the top of each column, specifically the main group or representative elements, we always know the number of valence electrons because of the group number, looking at the Roman numerals or the ones place of the 2 digits. Alrighty, so it's important that we know how many valence electrons each element has, because when elements go to form bonds, we're going to follow the octet rule, which tells us that atoms gain, lose, or share electrons to create full valence shells. And a full valence shell for the main group elements is an octet, which is 8 electrons. So when we talk about atoms gaining or losing, those are the ionic compounds. When we talk about elements sharing, those are the molecular or covalent compounds. So now let's take what we know about the valence electrons and apply it to the formation of these 2 different types of compounds. So for ionic compounds, it's actually a chemical reaction. So for example, if we wanted to look at the compound formed between magnesium and fluoride, we would write the Lewis structure for magnesium, and it was in the second column, so it has 2 valence electrons. Fluorine is a halogen, so it has 7. And so with ionic compounds, remember it's an electron transfer. It's a chemical reaction. We transfer electrons. Anytime we're transferring electrons, that's a reaction. So we'll use curved arrows to show this transfer of electrons. Now magnesium, it needs to get rid of both of these electrons to have a full valence shell. But fluorine only has room for one. So the first electron from magnesium goes here. We use a single barbed arrow to show that we're only moving one electron. And then we'll bring in the second electron to the other fluorine atom. So we have created now a magnesium cation. It has lost both of its valence electrons to have a full inner core shell. And we have created two fluoride ions. And so this is how we would use Lewis structures to show the formation of ionic compounds, right? Keeping in mind that then these ions will form the crystal lattice. If we wanted to write the formula unit, it would be magnesium fluoride. We would have a 1:2 ratio because it's going to take two fluorides, remembering that the electrons lost have to equal the electrons gained. So everything is balanced and conserved. Now let's compare this to how we work with covalent compounds. Because with covalent compounds, it's all about electron sharing. So it's approached very differently. So for example, if we had a compound methanol, CH3OH, here it's not a reaction. All the electrons are shared. So I'll show you briefly how to do the Lewis structure to compare it from methanol. However, there is a video tutorial on drawing the Lewis structures for covalent compounds. So if my explanation is too fast here, please take the time to go back over the other video. Alrighty, so carbon wants 4 bonds. Carbon and oxygen are the two central atoms. Oxygen wants 2. We know that these hydrogens are going to all be connected to carbon. And then we have the bond between the oxygen and the hydrogen. And using our bonding patterns, we know oxygen wants 2 bonds and 2 lone pairs. As a double check to make sure this is correct, let's do a valence electron check. With our carbon, carbon gives us the 4 electrons. Hydrogens, we have 4 hydrogens all together. They each give us 1. And the oxygen gives us 6. So we have 14 electrons. Let's double check the structure I've drawn to make sure it's correct. 2, 4, 6, 8, 10, 12, 14. So we've used the 14 valence electrons available for a compound with this chemical formula. We've observed all of the bonding patterns for neutral organic molecules. And notice here, all of the atoms are sharing the electrons. This is locked into a molecule, right? Versus up above, ionic compounds are also called salts. So salts create a crystal lattice, and these ions, remember, they can dissociate in solution to be independent, where the atoms of a covalent molecule are always locked together because the electrons are shared. So you want to get to the point that when you look at a compound, you recognize it as ionic or covalent. And the helpful way to do that is to keep in mind the stair-step line that's highlighted here. So even if you're looking at a periodic table that doesn't include the stair-step line, you always want to see it anyway. The elements to the left of the stair-step line are the metals, and to the right of the stair-step line are nonmetals. Whenever we see a compound that is a mix, right? So ionic compounds are typically a metal plus a nonmetal, whereas covalent compounds will be 2 or more nonmetals. And then last but not least, when we can then determine how the elements form these compounds by taking advantage of the fact that we know the number of valence electrons for each element by looking at the group number at the top of each column. So that concludes this review of valence electrons and the periodic table, and brings together several concepts that are introduced separately, but I think it can be helpful to see them in this way to support your practice in homework. So if you're struggling with some homework right now and this information was useful, go ahead and practice a few problems to reinforce your understanding.